Okay, so hi everyone. So first, let me thank the organizer of this nice talk and also the three people that organized this particular workshop, this specific workshop, which is very interesting. And we should take more time to discuss this kind of subject, I think. So I will illustrate a particular side of the trade-offs that Frédéric explained previously, which is you can go to nonlinear techniques when you find that using linear methods has some limitation. But in this case, to estimate your uncertainties is very difficult. So I will show it applies here. So I will apply it to dust CIB component separation from observational data. I will present it very quickly, and then I will go in the discussion of the uncertainties. So that's new kind of component separation methods we developed in the recent year at LPNS. So I say that to you, I will hide a lot of details under the rug, but we are very happy to discuss if necessary. So here you have an example of the Herschel field, okay? Spider field at 250 micrometers, okay? So basically what we see here is that we have dust thermal emission, and we have also the CIB, the cosmic infrared background, which is basically the signal emitted by the galaxy other than the Milky Way, okay? So the idea is, the question we ask ourselves is, okay, what can we do to separate both these emissions, okay? So let me fix the notation. We have D, the observational data, which is a mixture of S, the dust, and K, which will be here the CIB. Okay, and what we want to do is to use non-Gaussian information, the fact that the different fields have a very different texture, okay, to separate them. So indeed, it's very difficult to separate them with usual method using their different spectral energy distribution, because basically the two signals come from the same kind of physical processes, okay? So what we will do to begin with is to work at a single frequencies, because the lever arm we want to use is the different non-Gaussian structures of the processes, okay? So as it's very difficult to find realistic simulation, people do a very hard work, but we know it's difficult. So what we want to do is to work only from observational data. So that way we don't have to take care about the uncertainties from the models. That's a nice point, but it also makes a lot of things more difficult, okay? So what we will do is we will evaluate from observational data the statistic of the CIB, okay, from a particular patch of the sky. And from the image I showed you and the statistics evaluated from another patch of the sky, we will try to recover the statistic of the dust thermal emission, okay? And that's basically the project of one of our PhD students, Constant Octobre. So what can we do? We have the Lockman-Hall fields. I will show an image later on, 250 microns from Herschel. And basically, we have almost no dust emission from our own galaxy in this field. So from that single field, we can have the statistic of K, of the CIB, okay? That's what we will do, and I simplified a little bit, but we will make a deformation of the initial image in the pixel space under certain constraints, which are written from scattering statistics, which are nonlinear statistics, which are very informative and low variance. And under several constraints, we will deform this proxy of the true dust map to have an estimate of it, okay? And at the end, we obtain a new an estimate of the dust map on which we evaluate the statistics. So at the moment, we focus only on the statistics of the dust map. At the small scale, we know it's not deterministic. That's something we're working on. And let me remind you that we only use two observations, the spider field that I showed previously, and the Lockman-Hall field. So here, an illustration of what we have, the Herschel spider observation, where you have dust and CIB, okay? Here's at the Lockman-Hall field, where basically you see you have only CIB, and only using these two fields, basically we succeed to separate this given image in two fields, what we identify as the dust and what we identify as the CIB, okay? So basically in the statistical constraints that we put, we say that the dust plus other realization of the CIB should have the same statistic as the initial data. And the second component that we identify as the CIB should have the same statistic as the CIB we estimate on the sky, okay? So we have that, it looks nice, but what are the uncertainties? And that's exactly what was said previously. I mean, we succeed to make this component separation because we use nonlinear techniques, highly nonlinear techniques. But then when we want to evaluate the uncertainties, which are central to the expression of the result you have, it's a little bit complicated. So let me discuss that quickly. So as I said, here we have two difficulties. Basically, it's a highly nonlinear separation, okay? So you have to take that into account. You have to try to compute uncertainties in this framework. And also something which is very difficult is as we work only from observational data, basically we have only two maps from which we can try to estimate uncertainties, but it's very difficult. We don't have a complete model of the CIB. We don't have any model of the dust at all because that's a component we don't know. And we need to try to have a certainty from that, okay? So I will show something which is very simple, but I think in research, we have to begin with the simple things. So what we will do is the validation on mock data, okay? So we will perform a separation where we know the dust, okay? To do that, we want a surrogate from dust observation. We cannot take them from the sky because you have CIB. So what we do is that we take the same field, the spider fields, but from H1 data, okay, which trace the gas, okay? We know that the gas is quite correlated to the dust, so it should be similar, not at all scale, but at least quite correlated. And the advantage is that we don't have any CIB contamination from H1 data. Okay, so we have spectrometric data, a cube. Basically, we use a ROSA reconstruction to denoise it and to have a single map, okay? And it's lower resolution. So previously, we had more than 1,000 linear pixels in size. Here we have 300 pixels only, okay? So, but the advantage is that as we have smaller patches, basically we can cut the Lockman hole patch in a lot of different small patches, and we can try to use the different patches to have some evaluation of the uncertainties, okay? So basically, there are a lot of kinds of errors that appear, okay? For instance, we use a map to evaluate the statistic of the CIB, okay? So we identify what we can call an algorithm error, which is, imagine we have exactly the same statistic from the CIB in the map on which we want to do the separation and the map on which we have access, okay? If we do that, we don't have uncertainty from the fact that actually you have a variance when you consider some patches of the CIB and the statistic will vary on the sky, okay? We call that the algorithm error. And we also have the statistical variance from the fact that actually you have some estimate, some realization of the statistics on the field on which you want to do the separation, and you have some estimate of some realization of the statistics on the field on which you learn them, okay? So here you have what we call the model error. It's an error from the model of the CIB, which comes from the fact that basically you don't have the same statistics exactly. You have a variance, a variability on the image on which you do the separation and on Lockman hole, okay? So what we did, I won't enter the details, but basically the model error dominates on all scales, and that's what I will show. So basically what we can do, we have a patch, we have a huge CIB patch, we can cut it in a lot of small patch. We use one of them, okay, to be the true CIB we want to separate, and we use the other one to learn the statistic of the CIB and do the component separation, okay? And we do that, we use all the combination we can have, and we'll have some errors, okay? So here you have an example of the power spectrum, okay, as a statistic. In blue, you have CIB plus dust. In green, you have the dust. In orange, you have the separation, okay? You have, forget about the brown one. And at each time, you have the true statistics, which are in plain lines, okay? And in dash line plus 1 sigma, you have the distribution of the result obtained from the separation, okay? So already it is nice because we have a first access to a 1 sigma variability, to basically the variance of the statistics, and we have some idea of the bias that we have between the truth and the separate, okay? So basically we can do that on a lot of non-Gaussian statistics. So at each time there's the same thing. In green, you have the CIB, the true and the separated. In orange, you have the dust, the true and the separated. In blue, you have the mixture, okay? And you see here, you have the PDF of the increment for 4 pixel increment. You have the PDF of the pixel, and you have some RWST statistics. I won't enter the details, but just this slide to say that we are happy. We see that actually to introduce these nonlinear techniques help us a lot because we were able to make a component separation. And basically at all scale, but the smallest one, we are able to have a good estimate of the statistic of the dust. For instance, here you see that we are able to reproduce the probability distribution of the pixel. we're able to reproduce the probability distribution of the increment, so that's nice. So to conclude, okay, we used some mock data. We had some interesting errors, but basically in the true life, we have only one sample of the CIB because we use the whole set of data we have. So we have no direct variance assessment. The mock data, it's a smaller patches, okay? So how to extrapolate to larger patches? If you have larger patches, you have more sample, you have less variance on your statistics estimates. So basically you could expect to improve your result, but how you estimate that? The H1 map is not a dust map. So basically how to extrapolate to a component that we don't know, because the whole point of this component separation is to be able to make a component separation with at least one component that we don't know. So basically what we can do is we can extrapolate for all from the application we did on mock data. For instance, we can consider the variance from small patches of the CIB, try to extrapolate it to larger patch. But I mean, what's the better way to do so? How should we do to convince you that we have some relevant estimate of the uncertainties, about even the good order of magnitude, let's say? And otherwise, what other method could we use? Okay, so I will finish here. So thanks for your attention, and don't hesitate if you want to discuss component separation. We are very happy to share with you what we are doing.